Okay friends, so in that last video, I kept changing the number of bars on the histogram just to kind of get different looks at the same data set. And then I mentioned skewness at one point. You may have been wondering why I was goofing around with that so much. If you think back to a couple weeks ago, we were talking about when to use averages versus relative position in a data set. And it's always nice to know that a data set is roughly symmetric before trusting the average. Now, the quick, easy skew calculator is just a real ballpark of yeah, no, or unsure. But honestly, looking at a histogram, and you'll see this the more we go through statistics, but also definitely the more you get into inferential statistics if you go down that path. When you're looking at sample data like we are right now, small data sets, this is a fairly small data, so we got 39 countries in it. It can be roughly bell-shaped, but still have holes in it. And that's what I was just kind of doing. I was kind of clicking through the bars and like, okay, all right, even though there's this little gap right here, it still looks kind of bell-shaped. But part of me thinks to myself, okay, maybe though, there actually is that break on that large side, and those data points that we're seeing out there on the high side are actually unusually large. So my brain is saying, okay, I like the data, I think it's symmetric enough, I think I can trust the average. So we're going to use what I'm going to call, I guess, Outlier Definition 2A. We're going to measure data points that are greater than 2 standard deviations away from the average. This is a very commonly used outlier definition. We're going to find any data points in the data set that are more than 2 standard deviations away from the average. So what we have to do first is we have to know what the average of this data set is. So that's why we use the Excel calculator, and I've got it at 489 points. That is the average score of these 39 countries in the data set. We also need the standard deviation. I'm going to use the sample standard deviation because this is a sample of countries, and it looks like it's about 61. Now, 2 standard deviations is pretty much a universal, agreed upon range, distance from the average. We spoke about standard deviations a couple lessons ago, what it is and what it's actually talking about. So what you do is you start with the standard deviation, give it a multiple of 2, which is going to be 122 points. And then we create a range of values that are that far up and down from that average. So the low is going to be 489 minus 122, and the high is going to be 489 plus 122. Let's see if Sean can do this in his head sideways. 367. I think I did that right. 367 on the low, and 1, carry the 1. Sorry, you have to watch this. Carry the 1, 611. So that means we've set up now a range of scores from 367 points up to 611 points. What we're going to do right now is go back and take a look at what these points look like when we compare them to that graph. Okay, my friends, so I've now just reset the histogram to have 15 bars, the same minimum, max, and max values. Let's take a look at that 367 and the 611. Now, they're not going to be perfectly represented on these because the axis we have here is actually increments of about 20 units. But we can still get roughly where they are. So 367 is going to be just left of that 370. And the 611 is going to be just a scotch to the right of that 610. Now, if you consider all of the data points in between those two lines, those would be considered the typical values. In other words, the values that are close enough to average to not be deemed atypical. So any data points outside of that range would be deemed atypical
by this outlier rule 2A. So you can tell right away that there are no data points lower than 367. You can justify that by looking at the original data set itself, by just coming over here. The lowest data point we have is 388 in Morocco. So in other words, none of the scores were quote unquote too low. But how about too high? Well, coming back over to the Excel calculator, we know that anything above 611 is too high. Well, we do have a couple of those, don't we? We've got Singapore and Chinese to pay. So those two scores are greater than 611 points. So Singapore and Chinese to pay would be viewed as larger than typical.
Okay, so in case you're wondering why 2 standard deviations, there was a quiz a couple weeks ago where I actually had you looking at the percent of data points that are within certain numbers of standard deviations when data is roughly bell-shaped. And the very special one is 2 standard deviations that gets used a lot in a lot of statistical applications. And you're going to talk a lot about this in Math 244. We'll talk about it a lot at the end of 243 also, but you'll talk about it a ton in Math 244 if you go that route. 2 standard deviations from average captures about 95% of data when data is roughly bell-shaped. If you check our data, we have 39 total countries in our study. 37 of those 39 are within 2 standard deviations of average. Take a look at that percentage. Pretty awesome, huh? And it's one of those things. It's just, that's what bell-shaped data does. It captures about 95%, which you can also see this almost as a connection between outlier rule number 2A and outlier rule number 1. If 95% of data is within 2 standard deviations, that means 5% is going to be outside of 2 standard deviations. That sounds kind of like something you learned on one of your first homeworks in here, that rare events or outliers happen 5% or less of the time. Boom, there's a nice little connection there. But anyway, you don't have to use the percentages. I just wanted to explain to you more thoroughly why we use 2 standard deviations classically to flag outliers in bell-shaped data. Okay, now, in the next video, I want to talk about, well, what if you don't think the data is bell-shaped enough? Like in this particular data, we felt pretty good about it having a mound shape to it, a bell shape to it. But what if you didn't? Let's look at another way of identifying outliers. It's definitely a bit more numerical, but it fits more situations. Let's take a look.